Shall I tell you when you've got 5 minutes left?
Mm-hmm.
Yeah? Is that okay? Because it's 25 minutes, yeah?
Right.
So at 20, I'll tell you.
Sure, yeah, no problem.
Okay. Good morning, everybody. Welcome to the first session this morning. My name is Nick Barrett. I come from the French Atomic Energy Authority, and I've got the pleasure to chair this morning's session. We have quite a dense session, lots of talks. We'll be starting with an invited talk from Xi Liu from the Carnegie Institution, so here in Washington, if I got my geography right.
Yeah.
And he's going to be talking to us about the molecular dynamics of domain walls.
All right. Thank you for the introduction. I also would like to thank organizers for the invitation. So in this presentation, I will mostly talk about understanding the dynamics of domain walls with molecular dynamics simulations. By the end of this presentation, I will highlight some works about organic metal halide perovskites, which is a very hot solar materials. Just in case I run out of time, I would like to acknowledge my collaborators and rep at the University of Pennsylvania and many talented graduate students and postdocs from rep group. Ilya Greenberg, who's now in Bar-Ilan University at Israel, and Ron here at our Carnegie Institution for Science. Recently, we started a very interesting project, which I will talk about briefly. So I would like to start my presentation by looking at the very fundamentals of ferroelectricity. As we all know, a ferroelectric is characterized by the polarization electric field hysteresis loop. From this hysteresis loop, we can immediately tell the saturated polarization, remnant polarization, and most importantly, the coercive field, which is important for material design and device applications. Unfortunately, it is challenging to calculate coercive field from first principles. Of course, we can calculate the well depths of this double well potential, but the theoretical coercive field based on the well depths is orders of magnitude higher than experimental values. This is expected because this energy scale corresponds to homogeneous switching. In a real material, ferroelectrics usually adopt a multi-domain state, and the domain wall motion dictates polarization reversal process. That's because nucleation has much lower energy at the interface. Here I show the 180-degree domain wall and 90-degree domain wall in lead titanate. Therefore, this means we need an atomistic understanding of the intrinsic physics of domain wall motion at finite temperature. So here I show the computational modeling hierarchy. Here we have accurate first principle methods, but at this point, it is too expensive to do finite temperature, large-scale simulation for a long time scale. Here we have less accurate empirical methods, such as molecular dynamics simulations, which is less accurate, but is much, much more efficient than these first principle methods. The procedure we adopt is to use these first principle methods to optimize our force fields and use these force fields for large-scale finite temperature molecular dynamics simulations. In many cases, this second principle method work very well, can not only providing a qualitative description of domain wall switching process, but can also provide a quantitative estimations. So our model potential is based on two conservation principles in bond valence theory. So bond valence is a very useful empirical concept that describes the bonding strengths. We can calculate the bond valence from the bond length. R0 and CR Brown empirical parameters. They are already available for many different atom pairs. So the bound valence conservation principle states that the bound valence sum around an atom should be equal to its atomic valence. So this bound valence energy captures the energy penalty for both overbounded atoms and underbounded atoms. We can also introduce the concept of bound valence vector, which is defined as a vector lying along the bond with magnitude equal to the bound valence. So the vector sum is the measure of the Bragg of local symmetry, which is important for describing ferroelectrics. Our bound valence model potential is very simple with only 4 energy terms. Cooling interaction, short range repulsion, and these 2 energy terms from bound valence theory. Throughout the years, we successfully parameterized the force fields for lanthanide and bismuth ferrite, and recently we have a fairly accurate potential for barium titanate. So a typical force field has no more than 15 parameters. They work well and under both constant pressure and constant volume conditions. They can capture temperature pressure-driven phase transition. They reproduce DFT domain wall energy pretty well. All these energy terms can be pairwise efficiently. This enables mean atom simulation at nanosecond timescale, as demonstrated in yesterday's presentation. So the dynamic ferroelectric domain wall is usually understood as an elastic interface moving in a disordered medium, and defects can pin the domain wall. Here I show the theoretical prediction of domain wall velocity as a function of electric field. There are 2 regions. In the creep region, the domain wall velocity depends on the electric field exponentially and has significant temperature dependence. In the depending region, the velocity has no temperature dependence and has this close to linear relationship with the driving force. This behavior is confirmed in this experimental work. And the mu here is called dynamic exponent. And experimentally, widely ranging values have been observed, and they're usually attributed to different types of defects. However, we are really interested in the intrinsic physics, which is what will happen in the absence of defects. So this is a supercell we use to construct a domain structure with 90-degree domain walls. It's a 40 by 40 by 40 supercell. We can apply electric field along 100 direction to initiate a domain wall motion and then extract the domain wall velocity from molecular dynamic simulations. We carry out the simulations under a wide range of temperatures and electric fields. The goal is to reveal the intrinsic temperature and the field dependence of the domain wall velocity. So this is a movie from molecular dynamic simulations. So each arrow represents the local dipole within each unit cell. The movie will repeat again. So it becomes very straightforward to extract the domain wall velocity from these molecular dynamic simulations. So this slide summarizes the results of hundreds of simulations. It shows the velocity as a function of electric field. Very interestingly, it has 2 regions. Here, at the low field regime, we can see that domain wall velocity has very significant temperature dependence. But here, the lines start to overlap with each other, which is a signature of depending region. And we can also plot log v as a function of 1 over e to get this dynamic exponent. We find that mu is equal to 1. This is simply Moore's law, even though we didn't assume any Moore's law in our molecular dynamic simulations. So the take-home message here is that the domain wall velocity can be described with a nonlinear creep-like region and the power law dependent-like region in the absence of defects. Then what's the atomistic region for such intrinsic transition? We definitely need a nucleation model. Molecular dynamic simulations is still too complicated to really figure out the contributions from different energetic terms. But of course, it can be very helpful. So before I talk about the nucleation model, I would just quickly go over the mapping scheme we used to transform a non-180-degree domain wall to a 180-degree domain wall. It's a very simple idea. this is top view of a 90-degree domain wall, but we can transform the coordinates. The capital X is perpendicular to the domain wall. The capital Y is parallel to the domain wall. Clearly, the polarization component along capital X direction doesn't change across the boundary. The capital Y component is flipped by 180 degree. This is also confirmed by our MD simulation. Here I show the polarization profile across the boundary. The capital X component is actually quite smooth across the boundary. So this mapping scheme, in principle, can be applied to all different kinds of non-180 degree domain wall, offering a unified framework for studying ferroelectric domain walls. So in this transformed coordinates, we look at the interface, which we look at a 90-degree domain wall. In MD simulation, we found a nucleus, a diamond-like nucleus with very diffuse boundary, as you can see here, this yellow and green boundary. And this is drastically different from the Miner-Weiner model. So whenever we're talking about nucleation model, most people will still refer to this 1960 paper, which is a beautiful paper. The model, but we find that some assumptions, we need to double check some assumptions they made back in 1960. So in this model, they assume a triangular nucleus. A is the width of the nucleus. L is the length of the nucleus. So the nucleation energy has three terms: the polarization electric field coupling term, the interface energy, which is the sigma W, is the domain energy, and the depolarization energy, which comes from the Coulomb repulsion between boundary charges. But as you can see, this is not a charge-neutral model. And most importantly, they assume that the depolarization energy, which is characterized by sigma p, is much larger than the interface energy, which is characterized by domain energy. The consequence is, if you look at this aspect ratio, the equation for aspect ratio, because the sigma p is larger than sigma w, the A is much larger than the L is much larger than the width of the nucleus. However, in this 2002 PRL paper, it is already pointed out if we use DFT domain energy, using DFT domain energy will give an unphysically large nucleus and very slow domain velocity compared to those observed experimentally. So we did some very careful analysis and find that under physical boundary condition, the domain energy is actually much larger than the depolarization energy. So so this is a MD study of 180-degree domain published several years ago. What they found is that the nucleus is a diffuse B-weld square. So this B-weld shape, as you can see here, effectively reduced the domain area. Equivalently, if we assume a Miner-Weiner-like boundary, that means the effective domain energy is much smaller. If you look at the equation for critical nuclear width, regardless the limits we're working with, the value of the critical width is proportional to the domain energy. And if you look at the equation for critical depolarization energy, a smaller critical width means smaller depolarization energy. That's one factor. We can also look at the polarization profile. So this is DFT results for 90-degree domain wall, and as you can see, the polarization at a domain wall is actually much smaller than the bulk value. We find similar feature in our MD simulations. This has two consequences. First, smaller dipoles means a larger fluctuation and enhanced dielectric constant. Again, from the equation, a larger dielectric constant will give smaller depolarization energy. In a very recent PRL paper, it is also noted that the dielectric constant is enhanced at the domain wall. And secondly, the boundary charge, the magnitude of the boundary charge is basically the change of the polarization at the domain wall. A smaller polarization at the domain wall means smaller boundary charge, again, reducing the depolarization energy. Finally, the diamond shape also has some cancellation effect. As you can see, the repulsion is partially cancelled by the attraction between minus charge boundary and positive charge boundary. This effectively reduces this factor 2 here, because this factor 2 comes from the repulsion of between boundary charges. The polarization gradient revealed from molecular dynamics simulation is much smaller than the value used in Weiner paper. So we can do an even more quantitative analysis about about the effect of different factors. So we use a modified formula by introducing 4 scaling factors corresponding to the 4 factors I just discussed. Bevel shape, reducing the domain energy, reduce the boundary charge, enhance the constant, and the cancellation effect coming from the shape of the nucleus. We can calculate the nucleation energy as a function of nucleus area. The black line is the Weiner model. As you can see, it has a very large critical nucleus and very high barrier. But after using the correct boundary condition, it significantly reduced the size of the critical nucleus. If you look at the depolarization energy of the critical nucleus, it becomes much, much smaller than the effective domain energy. In another word, Weiner model and an assumption of large depolarization energy will give you a very large aspect ratio, but in a limit to smaller depolarization energy, which is consistent MD observations, the aspect ratio of the nucleus is actually close to 1. Okay, with this modified nucleation model, we can now explain the original creep and depending. Now we only have 2 energy terms, domain energy and the polarization electric energy coupling. And we can see that the size of the nucleus decays under higher electric field, and the nucleation barrier also decays as we increase the electric field. So when under low field region, the nucleation barrier is much larger than thermal fluctuation, and therefore Arrhenius dependence of rate on nucleation barrier is expected. On the high field regime, the size of critical nucleus can no longer be smaller. Therefore, the growth becomes the dominant step. In another word, on the low field region, the size of critical nucleus is shrinking, and when we increase the electric field, and of course we are generating more and more nucleus by the mu type. Therefore, we get an exponential increase. But here, the size of critical nucleus is almost constant. So this explains the intrinsic creep to depending behavior. Of course, we can have a more sophisticated nucleation model based on Landau-Ginzburg-Diversheim theory. Again, the first is energy gain for dipoles aligned with the electric field. The second term is energy penalty for creating new domain walls. It has local energy penalty and gradient energy penalty. I'm not going into details, but the key point here is that in principle, all the parameters can be estimated with DFT. So using this Landau-based nucleation model, we can quickly estimate the nucleation barrier using just a few inputs from density functional theory. With this nucleation model at our disposal, it becomes trivial to estimate the barrier as a function of. It becomes trivial to get a barrier under different temperatures and its relationship with electric field. The slopes gives us the activation field. So using this multi-scale scheme, we compare the temperature dependence of activation field from our analytical model and MD simulation agree pretty well. Now we have an approach to quickly estimate the activation field. Then what we can do with this activation field? As I demonstrated earlier, in the creep region, in a low field region, which is most experiments are down, the velocity follows the Merz law. Once we know the activation field, we can know the velocity under different electric field. Using this equation, which is basically a simple integration, we can figure out the change of polarization as a function of time. Here we assume that the polarization switching is realized through domain wall motion. So the only parameter we need is the size of the average size of the domain wall. So we apply this method to different ferroelectrics. Here I show the results for PCT and barytonate. Our theoretical Kursor field now is at least of the same order of experimental values. It also has this frequency dependence. I need to emphasize that Kursor fields in DFTs is probably not well defined because the magnitude of the Kursor field really depends on the frequency of the electric field. So now, this is, our method significantly improved the theoretical predictions of Kursor fields. Okay, now I'm going to switch to another project, collaborate with Professor Lane Martin at UC Berkeley. As we all know, string engineering is a powerful tool to control the domain structure in ferroelectric thin films. Our collaborators did a really nice work. They shown that it turns out the orientation of the substrate can also serve as a control knob for domain structures. So as you can see in this 001 and 101 oriented thin film, minority domains have polarization in plane. The most interesting case is the 111 thin film. You can see these highly nano-twinned domains. You probably cannot see back there, but believe me, within each band, there are two different polarization variants. And these different polarization variants have similar volume fractions. So what we're interested is how will the what's the domain switching process in these thin films. So we look at this, to model the domain switching process in 101 thin film, we simply take the volume fraction from experimental observations and apply the electric field along bar 1, 0, bar 1 direction, which is the same as the electric field orientation in experiments. So quickly show you the results. So when we, as you clearly see at 3 picosecond, we can see 180-degree switching at the boundary, as increase electric field, more and more 180 degrees switching at 10 picosecond. We turn off the electric field and let the system to relax. This is constant volume simulation. So at the end, we can see the re-emergence of the domain pattern that is similar to the initial domain pattern. So the finding is that the ferroelectric 180 switching is still the dominant mechanism in 001 and 101 samples. We found something very different in 101 thin film. In this case, the electric field is applied along 101 direction. As you can see, at 5 picosecond, we see a lot of 90-degree switching. As you can see, within each band, there are two different polarization variants, very similar to what observed experimentally. As we keep applying electric field, the whole band will undergo 90-degree switching. Again, 10 picosecond, we turn off electric field and let the system to relax. So if we compare the initial and the final domain pattern, we find that many dipoles undergo 180-degree switchings through successive 90-degree switching. We know that 90-degree switching is ferroelastic. Then why this kind of ferroelastic switching can happen in thin film, which is clamped by the substrate? I think this is because whenever there's a 90 switching chain A to C, there's a compatible switching chain C from A. Therefore, macroscopically, the elastic cause is not that big. Recently, I started a project with Ron, so in this 2004 Nature paper, Ron found that in aged barytonate, has a giant electric field-induced strain. He proposed that in aged ferroelectric, the defect dipole will align with the bark polarization. We can apply electric field to switch the polarization by 90 degrees. This will give rise to a huge strain change. The most interesting part is once we turn off the electric field, the defect dipole will try to rotate the polarization back to its initial state, making this strain change a recoverable process. So we want to show this whether this magnetism is really possible. In theory, we designed a defect model in the context of molecular dynamics relations. We implicitly introduced a dipole at B site. What we found is with larger defect dipole, the switching field becomes larger. And if the magnetic dipole is not enough, once we turn off the electric field, there's no strain recovery. On the other hand, if the dipole is large enough, even with a 2% doping, you can clearly see the spontaneous strain recovery. The C-axis will recover to its initial state. I only have a few minutes left, so I will quickly highlight some of my work in hybrid perovskites. So hybrid perovskite has lead at the center of the cube, iodine at the face center, and an organic cation at A site. The power conversion efficiency is improved rapidly in the last maybe 2 years, as you can see here. So this is really transforming the research of photovoltaic. So I look at the domain walls in organometal hybrid perovskites. Depending on our relative orientation of the molecules, we can have uncharged 180-degree domain wall and charged 180-degree domain wall in this material. Because this dipole is very small, it turns out the charged domain wall has a relatively small domain wall energy compared to possible charged domain wall in inorganic ferroelectrics, such as lead titanate. What we found is that for supercell with charged domain wall, it will have a smaller band gap. I think the most interesting part is that this charged domain wall will create this potential step that will help electron-hole separation. Even for uncharged 90-degree domain wall, there's a potential step across the boundary because of the polarization discontinuity. And similar polarization step is also found in 90-degree domain wall lead titanate in 2001 PRB paper. So the take-home message here is the domain wall, because of the polarization gradient, can create a built-in electric field for charge separation. In the last slide, I will just quickly introduce a new concept, which is ferroelectric topological insulator. Topological insulator is a quantum state of matter that has insulating bulk state, but metallic edge state that is protected by a symmetry. But in most cases, topological insulator has very small band gap, but as we know, ferroelectric usually have very large band gap, so it's kind of challenging to find a material that can support both properties. We find that for cis and lead iodine and certain strain condition, it can be both ferroelectric and topological insulator. It has very interesting topological surface states. So put it simple, the P- surface state will give rise to a P-type direct cone, and the P+ surface will give rise to an N-type direct cone. Okay, I will conclude. I will stop my presentation here, and thank you for your attention.
Thank you very much for this talk, which covered a very broad range of problems concerning domain walls. We've got time for a couple of questions. There's one here.
Comment. Excuse me. Very interesting talk. Let me make small comment. Just after developing by Ginzburg the phenology of Landau-Ginzburg in '49, Ginzburg is my teacher.
Yeah.
My name is Professor Friedkin.
Yeah.
Yes. It became clear that Ginzburg value for coarse field is much bigger than experimental values. Mm-hmm. But when we, with Professor Ducharme, got very thin perovskite films in approximately a few nanometers thickness, mm-hmm. we got Ginzburg value of coercive field. And it's very good, could be explained, not by the pinning and the pinning mechanism, but by Landau-Halatnikov equation in frame of Landau-Ginzburg phenomenology. You see, if you have films with thickness which is very near to the critical size of domain, the size of critical nucleus of domain, there is no space for domain process. You can have nucleation, you can have initial stage of growth, but you cannot, such process which was investigated by Kolmogorov, Avrami, Shibashi. You understand me?
Yeah, I understand.
So it is two possibilities to explain this behavior at very high coercive field, which is equal to Ginzburg value. The pinning mechanism, or it is the mechanism which is developed by Ducharme and myself. I recommend you to take the book which we published recently, Ferroelectricity at the Nanoscale, Springer, 2013. Let us discuss more.
Yeah, I definitely understand your comment. You're saying when the thickness of the film is smaller, even smaller than the size of the critical nucleus, then probably homogeneous switching becomes the dominant mechanism. And in that case, the depth of the double well potential, even though it gives a pretty large coercive field, starts to make sense. But I'm just, my comment is sometimes in this work, we're of course interested in Barker response, but for a thin film, when it's too thin, is that really a Barker property? Or, so I think the idea of homogeneous switching is definitely very interesting, and it's also part of future research.
If you indicate a few microns, 1 micron, the coercive field is definitely much, much less than Landau-Ginzburg value.
That's true, yeah, and that's also
Yeah,
what we found
absolutely.
here. Yeah.
The value of Landau-Ginzburg you obtain for perovskite in the nanoscale region approximately, because the critical value of domain is approximately, in accordance with Weinreich, 5-10 nanometers, that for this scale you can obtain the real Landau-Ginzburg value. And switching is described by Landau-Halatnikov equation.
Thank you. Just one quick question on the other side of the room.
Yeah, my question is closer to your simulations that you reported in the first part. So if I understand correctly, you always consider the domain wall to be exactly parallel to a high-index crystal plane.
Right,
so
right.
then you always have the problem of nucleate, nucleate, nucleate. So can you do simulations at which you off-cut, let's say at 2 or 3 or 4 degrees, and then you just have pure flow? I'm curious how the results would depend.
In theory, yes. In theory, yes, but that is more about technical difficulties because of the periodic boundary condition. Yes, in theory, we can do those simulations. But I think in experiments, in most cases, at least for if you just care about the coercive field of a material, in most cases, just those like 180-degree domain or 90-degree domain that really matters. There's no high-index domain wall.
No, but it was off, wouldn't most of them be off by a few degrees?
Worth checking, yeah.
Yeah,
Thank you.
This is quite a rich subject. I think you're going to have a lot of questions in the break. I would like to know what happened when you put a surface in there as well. But for the moment, let's thank the speaker and move on. So our next speaker is Jacob Chapman from UCL in London. Is that right? So if the title hasn't changed, you're going to be talking about ferroelectric nanobubble domains in prototypical thin films, strained thin films. Have you got the microphone? Do you need
Okay, great. Okay, so hi, my name's Jacob Chapman, and I'm here representing University College London and the National Physical Laboratory in the UK. So this is a collaborative project that we're working on between the two institutions at the moment, mainly looking to develop the properties towards building piezoelectric transistors. So my work's being supervised by Anna Kimmel and Dorothy Duffy between these two. And today I'm also presenting some results which we have done in collaboration with Marty Gregg and Alina Schilling at the Queen's University Belfast. So quickly, what are the motivations for my research? I'm doing quite a broad range of things at the moment, but today I'm going to focus on this work here to do with strained prototypical perovskite films. So first off, what is the National Physical Laboratory? It's the UK Centre for Metrology. So they're basically aiming to improve measurement techniques to be able to develop traceable measurements to be ordered to help develop the next generation of technologies. So this is the type of stuff that we look at. So I'm part of the Mathematics Modelling and Simulation group, which again does a wide variety of things. But I'm focused here on the atomistic modelling. So basically my role as part of this team is to kind of look at these things from the ground up using both first and second principles modelling. So that's what I'm going to be talking about today with some of our work relating to this piezoelectric transistor. So ultimately this will be using a PZT. And we have a very good model for using molecular dynamics for PZT, which has been derived by my colleague. But rather than jumping straight in and modelling millions of atoms to actually simulate the actual transistor, I decided it was best to actually, check this model works properly far from the equilibrium conditions that it was derived. So in the literature, there's a lot of results regarding PTO thin films, so I thought that's the best place to start. So quickly about the model, like I said, it was derived by my colleague Oliver Gundelli. So I'm using the PTO component of this PZT force field, which reproduces properties very well. So it uses molecular dynamics. So here we set up our system of atoms. We evolve it using classical Newtonian mechanics. And obviously our particles are interacting. So we represent our short-range interactions through this Buchanan potential here, which favours the short-range like centrosymmetric, high symmetry configurations. And then we've got charged particles, so we've got this Coulomb interaction. And then also, because we're dealing with ferroelectrics, obviously we want this intrinsic polarization. So how do we model that if we've got particles? Well, basically we split it up into three components. So we represent the nucleus as a massive core, we represent the electron density as a spherical shell, and then we tether the two by a spring. And we use here this isotropic and harmonic spring potential, which helps to stabilize the ferroelectric phases in this model. Okay, so that's great. So now we can evolve our system for various temperatures, etc. And we can see that we reproduce the phase transition mechanism, the phase transition for PTO. We reproduce the spontaneous polarization and the correct properties as we evolve with temperature. So that's great. And then we can also, so I just quickly wanted to say, this is how we can calculate polarization here. So if we take the average, the ensemble average, we can calculate polarization using a p-cation center conventional unit cell, use the titanium core as our reference, and then look at its 29 neighbors and calculate the dipole moments. And there we go, we have our polarization. Okay, so like I said, I wanted to look at these PTO thin films. There's quite a rich amount in the literature, so I wanted to check this. So how do I set it up? Well, first off, I wanted it to be PBO symmetrically terminated because this is the more stable termination, which has been observed in the literature, and we also check for our force field. That's great. And then also, so what we do is we set up this periodic cell. So we set up this vacuum region, make sure it's large enough so that our slab doesn't interact with its periodic images. And then because we have these open circuit boundary conditions, we need to make sure that our outer plane polarization is 0 to make sure we don't get this spurious displacement field across our system. So we initially set up a system with ideal Cattell domains facing up and down along the x direction here. So this is how we set up our initial simulation cell, the idea being that we can ramp up the temperature, cool it back down, see what domain patterns we get. But we also wanted to look at the misfit strains. So we can do this without affecting the degrees of freedom of any of our atoms, just by fixing our simulation box. So we use this canonical ensemble, and by fixing the shape of our cell, we can change our misfit strain values. So basically the idea being that for a fixed strain value, we can increase the temperature and see what domain patterns we get. And does our model agree with the literature? So this is the results we get. So this is using a 10 by 10 by 10 simulation cell, so quite small, but for the thickness of the film, that's actually good agreement because our model also satisfies the Cattell scaling law to do with domain thickness. So this was an ideal size to use and has also been used in the literature. So what we find in the high tensile strain, we get these AA domains here, which are these 90-degree domain patterns if you're looking up from the surface. Equally, it can also be facing along the 110 direction. So basically using our definition here, so long as the macroscopic polarization is along 110, that seems to satisfy this rule. If we go into this high compressive region, we get these what we call CD domains, which are these Landau-Lifshitz looking closure domains, which have these 180-degree domain walls with these 90-degree domain caps. If you make it thinner, agreeing with the work by Sylvia Tinter's group, this reduces down into a vertex, so you get these vortices. If you increase the strain temperature, back towards the freestanding limit, you get this transition path where you go into these BCD domains, which has the same cross-sectional profile as the ABC, as the CD domains, but has this in-plane component. And then you get this ABC domain pattern here, which has this kind of like continuous dipole wave along X, as well as an in-plane component, while maintaining these closed domain-like patterns. Okay, so that's great. Like I said, I wanted to compare to the literature. So how are we doing so far? Well, in the literature, we found these AA domains, these ABCD domains, CD domains, and also this high, obviously the Ferroelectric domains at high temperature. That's great, that's exactly what we wanted to see. But then we also found these CB domains, which, as far as we could see, hadn't been observed for these PTO thin films. So here we are, we call them CB because they're C domains, they're in and out of the planes, this is from the surface, but they're kind of bubbles rather than being, like tubes like they are here. So we wanted to look at these. What are these? Is it just an artifact of our force field? We weren't too sure, but we decided to take a look. So if we look at the polarization maps at the center of the film, so here, if we look at our cartoon, we see that we've got these 180-degree domain patterns, like was suggested by Streifer a long, long time ago. But then as we get towards a Curie temperature, we find this diffuse nucleation, like was talked about in the previous talk, where you get these beveled-like domain wall nucleations, which then propagate, and then as a consequence of our open circuit boundary conditions, this causes buckling of the domain wall, so it's no longer along the easy axis. So we get this phenomenon of domain wall wandering, which has been observed in PZT recently and experimentally in the literature. So then as you get even closer to the Curie temperature, you've got these stable, bubble-like domain patterns. So I wanted to ask myself, has this been observed? And the answer is yes, under short circuit boundary conditions. If you apply an electric field, under certain conditions, similar bubble domain patterns have been found. So that means, this is fairly good evidence that our model is actually onto something and isn't just, making it all up. That's great. So we showed this work to Marty Gregg and Alina Schilling, and they said, hey, great, you know what, we've actually seen very similar domains in BTO. So here is some PFM results that they sent me. So this is flux-grown crystal of BTO, right near the Curie temperature, and they found that what was originally 180-degree domains breaks off into these bubble-like domain patterns. So if we look at my simulations here, I've plotted the positively polarized out-of-plane dipoles. We see excellent agreement, really, and this is the polarization map from this simulation at the center of the film. So we see really good agreement between these two simulations, between the simulation and the experiment. So now you might be wondering, is this physical? Can we really compare this bulk experiment to our thin film calculations? And the answer is yes, we think so. Why? If we go to the work of Kanzik, 60 or so years ago, way ahead of his time, he realized that in these materials you get this skin layer. So what is the skin layer? It's approximately 10 nanometers thick. and it's where the properties are distinctly different from the actual bulk of the material itself. Okay, so that's cool. Different. It's a very thin layer at the surface that we're actually imaging using the PFM. So then we actually wanted to check this, so we used transmission polarized optical microscopy and actually confirm that the bulk of the crystal was actually ferroelastic AC domains. So these bubble domains that we're observing at the surface with PFM is distinctly a surface effect on a very thin film at the surface. Further, from Kanzig's work, we also know that the misfit strain of this surface layer is smaller in the tetragonal phase below the Curie temperature. So we actually know that this is actually under somewhat compressive strain. So if we remember, that's the same conditions that our film was under when we observed bubble domains. So what does this mean? It means we've got the same conditions. We've got a very thin film under compressive strain. And again, in our calculation, we had a thin film under compressive strain, which sees these remarkably similar domain patterns. So that's great news. So being confident that our model is actually working, we can look at a few other things which are quite interesting. So we wanted to look at the in-plane polarization. Is it homogeneous in these BC domains? And the answer is no. Actually, if you scan across the in-plane polarization, going across X towards the domain wall, we find that the in-plane polarization is enhanced at the domain wall. So you've actually got this plane of ferroelectricity right at the domain wall interface here. Similarly, in the ABCD domains, here what are called chiral bubbles in the literature, we actually find that the polarization is enhanced around these chiral centers. So we've actually got these concentric tubes of enhanced ferroelectricity. So if this is true, this I think could have potential quite a lot of good applications industrially, which is quite interesting. Okay, so to conclude, we looked at the misfit strain versus temperature, or a Pertsev map of a PTO symmetrically terminated thin film. We've got very good agreement with the literature. But we also discovered this new domain pattern here, and we've got experimental evidence backing that up. So thank you very much for listening.
And thank you. We've managed to catch up a little bit on our timing. Thank you for the interesting talk. Questions?
Thank you. It's beautiful work. I remember when we were looking at this nanobubble in PZT, for instance, we find that sometimes they form like arrays, hexagonal arrays. Did you have also like that in the simulation, some kind of self-organization between the nanobubble domains?
For the smaller cells, that seemed to be how it was. But that's why I increased the simulation size, because I wasn't sure if it was an effect of periodic boundary conditions. It seems to be a little bit random. I mean, you can somewhat see here, it retains a little bit of the history of where the 180-degree domain wall was. If I increase my simulation time, so this was over 80 picoseconds or so, if I increased it into nanopicoseconds, perhaps it would stabilize into a distinct array, like you said. But that's something I'd actually have to check.
Next question.
How do you treat the surface depolarization charge? Because on the ideal open circuit condition.
Yeah, so like I said, it's completely uncompensated at the moment. So this is why I had to form this Kittel domains. But it's something that we're actually working on at the moment. In our current model, we're developing a way to actually be able to tweak this and actually change our depolarizing field using like a platinum, Finnis-Sinclair type model to actually change this.
Time for another question. I've got one which is very naive. If you always start with out-of-plane domains.
Yes.
If you start with in-plane domains and a compressive strain, do you get to the same result? Has that been tested?
I haven't checked that, but I'm pretty sure I would. Reason being, if I make these films really thin, it spontaneously turns in plane and becomes an A domain. Secondly, I started with these 180-degree domain walls. Under tensile strain, it reorientates in plane and becomes these 90-degree AA domain patterns. So I expect it will do a similar thing. I expect the 180-degree domain patterns under compressive strain would be the more favorable ground states. It would automatically find its way into that type of domain pattern.
Okay, thank you. Well, if there are no further questions, let's thank the speaker again. And the next speaker is Guillaume Nataf from the Luxembourg Institute of Science and Technology. And his talk is entitled Experimental Evidences of Defects Stabilized by Neutral Domain Walls.
Now it's better. Okay. So, first of all, I would just like to thank the organizer for giving me the opportunity to present my work on the interaction between defects and domain walls. So I did this work in Luxembourg Institute of Science and Technology. There has been recently growing interest for domain walls in ferroelectric and ferroelastic materials. The main idea is that domain walls sometimes have different properties from the bulk, and so domain walls could be and could become the active element instead of the bulk in this material. So I just give a first example with a ferroelastic material, well known is calcium titanate, and this is a 10 image of a domain wall. And the arrows just represent a small shift of the titanium atom in the vicinity of the wall. So it means that it is an evidence that at the wall you would have polarity while the bulk is still non-polar. Second example, well known now, it's in bismuth ferrite, insulating material of course, where people found conductive domain walls. So this is first a PFM image where you see different domains with different domain walls, and below you have a conductive AFM image of the same area, and you see that only the domain wall and actually only some domain walls are conductive. So the question then is, why do we have conductive domain walls? If you look at paper and the first papers on the topic, you always find the same explanation. So in bismuth ferrite, you always find some explanation based on the role and the key role of oxygen vacancies. And you need, in this case, to have segregation of oxygen vacancies at the wall. And actually, later on, people found conductivity in lead zirconate titanate oxide. And again, the same explanation. Because of oxygen vacancy segregation, you can have some conductivity at the domain wall. But more recently, there has been an experiment on lithium niobate. And they also found conductive domain walls under illumination. So this is just the setup. You have a bottom electrode, you have the sample with 180-degree domains. You scan with your AFM tip and you illuminate at the same time. So the PFM image of the domain is expected. This is 180-degree domains. And below you see that you have conductivity only at the wall. And actually what is not shown here is that you have conductivity only if you put some UV light on the sample. But in this paper, the explanation for the conductivity is absolutely not based on oxygen vacancies. I mean, the word oxygen vacancies does not appear at all in the paper. So the question then is, why do we have conductive domain walls in this case? And this has motivated my studies, actually. So just a quick reminder on lithium niobate. It has a very high transition temperature. So it means that you can study it in a wide range of temperature without really problem of phase transition that is nearby. You have only two types of ferroelectric domain walls, ferroelectric domains. They are related by the Gaussian movement, so mainly the lithium movement downward if you want to reverse the polarization downward. And one very important point is that most of the time you do not have stoichiometric lithium niobate crystal, single crystal. You quite always have a congruent composition, so it means that you have a lot of defects in your sample. actually most of the defects are niobium antisites, so instead of the lithium here, you just put a niobium atom. And for charge compensation, in this case, you just put lithium vacancies, so you just remove some lithium atoms. So this is kind of good system. We have a simple domain structure, only 2 kind of domains, and we have a lot of defects. So to study the interaction between defects and domain walls, it was a good idea. And what we did first is we did dielectric spectroscopy, because it's a well-known technique to study defects. So we just studied a single crystal of lithium niobate without domain wall, so it was a monodomain of lithium niobate. We did dielectric spectroscopy as a function of frequency and temperature. Here I just show you the dielectric loss as a function of frequency for 3 different temperatures. You see that you have something almost flat, except an increase of the loss at low frequencies, and this increase is higher at higher temperature. This was fine, this was the result we expected. And then to check, we ordered a new sample from another supplier, and surprise, we have a peak now in the dielectric loss, while it's again a monodomain sample without domain walls. So we just did some annealing of the sample, and we looked at it again, and this peak vanished, and we finished with the same dielectric spectrum we had for the other sample. Then we decided to study precisely in temperature what was going on. So it's just the same for different temperatures. You see that with increasing temperatures, the peak position shift to higher frequencies. And actually, if you take the frequency and you plot it as the inverse of temperature, you find an Arrhenius law that match more or less with an activation energy that is very small, 0.18 eV. With this in mind, we decided to study domain walls. So we went to a sample with a high density of domain wall. We call it periodically poled lithium niobate. It means that you have domains with a period of 20 to 28 micrometer. This is just an optical image of the sample, and you see all these are domains, and in between you have domain wall. So this is a sample with a high density of domain walls. We did dielectric spectroscopy, and we found exactly the same peak, still at the same frequency, around 10 kilohertz. But with 2 main differences. The first one is that when we anneal the sample, we still have the same relaxation with the same amplitude and at the same position, even if we anneal at 800 degrees. Second difference, the peak position does not shift when increasing temperature. So if I just summarize, in the first sample, without domain wall, no relaxation, no peak in the dielectric loss. In the second one, we had a peak, but it disappears if you anneal the sample. And in the sample with a high density of domain walls, you find the same peak in the dielectric loss, but without temperature dependence. So if I come back to this activation energy, it's very small. I mean, 0.18 eV. It cannot come from the motion of ions in the sample. If it was lithium movement, for example, it will be above 1 eV. So it must come from some electronic state in the sample, and in some niobate, one possible idea that it comes from polaronic states. Then when you anneal the sample, you will rearrange the structure, and that's why the relaxation vanish in the sample, and you have kind of new defect thermal equilibrium. But in the periodically poled sample with a high density of domain walls, since you still see this relaxation, this is a strong evidence that domain walls will stabilize these polaronic states. So then we wanted to have a more local picture. So we went to Raman spectroscopy. Again, this is a technique that is well known, that is sensitive to defects, and you can have spot size below 1 micrometer to get local information. Instead of studying only one sample in the congruent composition, we added dopants to just increase the defect and change the defect structure in our sample. So we doped between 1% and 7% of magnesium. This is a typical Raman spectrum you would get. It will not change a lot with doping. I will focus actually on 3 modes, so just their name, ETO1, ETO8, AL04. You do not have to remind this. what you see is that with doping, the peak width of all this mode increases. And this is expected because you just increase the disorder. You put magnesium in your sample, so peak width increase. But you also have a trend for the peak position. You see that the trend is not the same for all the peak. For ETO1, you have almost an increase of the frequency with the doping. For ETO8, you have a decrease, and for A04, either no real trend or slight increase of the frequency. So now that we know what is the influence of magnesium on our Raman spectra, we decided to go to study domain wall. So actually in lithium niobate, you can see domain walls in an optical microscope. Due to the strain, you can find them. And what we did then is that we did many Raman spectra across the domain wall. So every 100 nanometer, we took a spectrum and across the domain wall. And what we get is the following. So I just show it for ETO1 mode, for example, to start. I go from a reversed domain, so I reverse the polarization by applying an electric field at room temperature, and I go across the domain wall, and then I have the virgin state of my sample. What you see, well, first you see that at the domain wall, something is happening. You have a change of frequency at the domain wall. But this is not the only feature you see. You also have a change of frequency between domains. This is not expected at first. And you also have some kind of different behavior depending on the doping level. Below 5% or above 5%, you do not have the same behavior. And if you go and study another mode, A04, you see that you also have a different trend. So if you compare 7% of dopants, in both cases, this is not exactly the same trend. So first, considering the difference of frequency between domains, actually this is known. This is due to defects. In lithium niobate, defects are arranged in a way that this is polar defect. So this polar defect will have a polarization, and this polarization will be in the same direction as the main polarization of your domain in one case, and in the opposite direction in the other case. And so this is a small internal field, a small difference in polarization that gives the small difference between domains. And we did not really want to study this point. It was already known. So what we did is that we annealed the sample at 200 degrees for 8 hours, because we know that in this case, the polar defects will realign with the main polarization. And this is exactly what we observed. You do not have any contrast between domains now in the peak position. But you still have a contrast at the domain wall. And actually, this contrast is still changing with doping. So I will just do some hypotheses to try to understand why do we have this contrast. And I will see if it matches with our observation. So first of all, we have a doping dependence of the peak shift at the domain wall. So it means that it cannot be due only to the change of polarization at the domain wall or to the local electric field at the domain wall, because it would be almost the same for all the dopants. Secondly, we have a change of sign of the shift. It was negative below 5% of dopants, it is positive above. So this means that a picture where you just have a reduction of the depolarization field in the vicinity of the wall, and that would be different for different dopants, does not work. It would just reduce the amplitude of the shift, but it cannot explain the change of sign. And if we look at the peak width, it does not change at the domain wall for ETO8 and A04 mode. So since we know the signature of defects from our first measurements, we know that it cannot be due to a dopant segregation. So I think that one explanation that remains is that what we see at domain walls are the signature of polar defects. And the fact that after annealing, we still have this signature only at domain walls while it disappears in the domain means that we have domain walls that stabilize polar defect structure. So just to summarize, in the electric spectroscopy, we have evidence that domain walls stabilize polaronic states. In Raman spectroscopy, we have evidence that domain walls stabilize bigger defects, this is polar defect complexes. So I think that these 2 points mean that you have a lot of defects at domain wall, and this has to be taken into account if you want to explain the conductivity at domain walls. Thanks for your attention.
Thank you. We've got time for a few questions. Ron?
Yeah, so I don't think you mentioned, but a corollary of this is that your domain walls are going to only move at the speed, I guess, maybe that the defects move, or at least they'll slow down depending on temperature. So has that been looked at in the experiments? You know?
I know there are some experiments where they look at domain wall motion. I do not think they really find a law linked to this, and if they are able to know if due to defect or not. But lithium niobate is one of the samples where you have strong evidences of pinning of domain walls at the surface and really bowing of the domain wall on defect. So there is obviously a link between both and some clipping.
So you mentioned that you can see the domain walls under an optical microscope because of the strain. How does the strain affect your measurements, especially the Raman measurements?
Well, it will play a role. Actually, if you see defects, sometimes you also strain the lattice. So do you really directly see the defect, or do you see the strain? It's the first question. But again, the strain at the domain wall cannot explain the change of sign with doping. The main idea, I think, is that I do not say that the signature I have is only due to defects. It's probably not. It's obviously not. But it's defects and more things that you have to add, like small strain in the vicinity of the wall.
Just maybe one question. Is the width of the change in the Raman spectrum due to just the spot size, your diffraction limit? Or does this strain field really extend a micron into the domain?
Well, it's not easy to say. We are just at the limit. So it's around 1 micrometer if you take the full width at half maximum of the peak. So we do not know if this is only the domain wall or if you have defects, segregation on a larger scale than just the domain wall.
One last quick question. If not, we thank the speaker again and we'll move on. So the next speaker is Vincent Garcia from the CNRS Thales Joint Laboratory in France. And I'm going to have to read his title. It's quite ambitious. Learning through Ferroelectric Domain Dynamics in Solid-State Synapse.
Okay, good morning everyone. So I will talk about learning through ferroelectric domain dynamics in solid-state synapses. And what I'm going to talk about is based on ferroelectric tunnel junctions, where we simply use ferroelectric materials as active tunnel barriers. And in these devices, the information is written by applying a voltage across it and is read by a simple resistance measurement. So why can we have different resistance states depending on the orientation of the polarization? We believe it's mostly related to electrostatic effects. So if we consider a tunnel barrier in between two different materials or different interfaces, we have different screening properties on both sides, and the polarization will induce an asymmetric variation of the potential profile. So now if we reverse the polarization with an electric field, this asymmetry will be reversed. And the consequence is that the average bar height of the tunnel barrier will be changing depending on the orientation of the polarization. And as tunneling depends exponentially on this bar height, we can have large changes of the resistance related to the switching of polarization. And so this is called tunnel electroresistance. Another advantage of ferroelectrics is that, as you've seen in the other talks, the switching usually occurs through the nucleation and propagation of domains. So this means that we should be, in principle, able to stabilize non-uniform configuration of ferroelectric domains and move from binary information to, this is not, okay, sorry. Yeah, move from binary information to multiple state switching or even memory stores. So why are we interested in these memory stores? In the lab, we are interested in this because of brain-inspired computing. We know that artificial neural networks outperform the performances of conventional von Neumann processors for key applications such as pattern recognition or data mining. So nowadays, there are software versions of these artificial neural networks that have recently produced breakthrough in facial or speech recognition from companies like Google or Facebook. But these simulated artificial neural networks require a lot of conventional processors and for days. So if we were able to fabricate these networks directly on a chip, this would make it much more power efficient and practical. So the basic idea is to be able to make a brain on a chip. So if we talk about the brain is made of two fundamental units, the neurons and the synapses. And in the human brain, for example, there are 10 to the 11 neurons, and each of them is connected by 10 to the 4 synapses. So this shows that this architecture is massively parallel. And learning is achieved by the ability of these synapses to reconfigure the strengths by which they connect two neurons. And this is called the synaptic plasticity. So if we want to make such kind of networks on a chip, we need to find a nano device that possesses such synaptic plasticity. And a good candidate for that is the memory store. So the memory store is a simple two-terminal nano device that can be finely tuned by voltage pulses. So in our case, we'll use this ferroelectric tunnel junction as our memory store. So as a ferroelectric material, we chose bismuth ferrite, and you heard a lot about bismuth ferrite, especially yesterday. And this material can be even in another phase called the T phase by stabilization with high compressive strain. And in this T phase, the polarization can be even bigger than in the bulk. So we fabricated thin films of this T-phase BFO using yttrium aluminate substrates and calcium cerium manganite buffer electrode. And the films were grown by pulse laser deposition. So in collaboration with Maya Marinova from LPS, we investigated the structural properties of these films by scanning transmission electron microscopy. These are cross-section images. We observed a sharp interface between the ferroelectric and calcium cerium manganite, and also a large C/array ratio in bismuth ferrite, and this is for a film of 10 unit cells. So we have already the signature of this T phase from the large C/array ratio. We can also have some information on the polarization by looking at the cation displacement. And here we found a displacement that is negative, which indicates a polarization pointing towards the CCMO. And this displacement is quite large, of the order of 40 picometer, which represent values of polarization of the order of 100 microcoulomb per square centimeter. So in addition, what they did is to have some information on the electronic properties at the interface by using Hills spectroscopy. And they correlated the manganese L3 chemical shift with the concentration of dopants in the films. And what they found, I won't go through details, but what they found in the end is that there's an excess electron density at the interface between CCMO and BFO. And when we integrate this corresponds to ranges that are quite close to what we observed previously from the cation displacement. So there's a large polarization in BFO that is initially pointing towards the CCMO, and we can directly visualize the screening carriers in the CCMO. So this polarization pointing downward is confirmed by PFM, and we can switch this polarization. And from these heterostructures, we fabricated fully patterned tunnel junctions with a chip here of 50 devices that we can connect with standard RF probes. And we obtain a high yield of working devices, good endurance and retention properties. But if we want to investigate the ferroelectric properties of these films, we need to find a way to visualize this domain. So we moved backward for a simple process where we have a unique step of e-beam lithography on a continuous layer of bismuth ferrite. And we have nanodots of top electrodes that we connect with an AFM tip so that we can do pulse measurements and measure the DC current at low voltage and do PFM through the top electrode to map the ferroelectric domains. So this is what we typically observe in this film. So this is the hysteresis of the remanent resistance as a function of pulse voltage. And for each step, we can stop and do resistance maps. So what we observe is initially we have the downward polarization state here and high resistance. At a certain negative voltage threshold, we reach state number 2, and this is corresponding to the nucleation of a domain with upward polarization. And then when we reach the on state, we have a majority of upward domains in this junction. So the switching from these two states, 1 to 4, is related to the reversal of polarization from downward to upward. And this is reversible with positive voltage pulses. We progressively increase the resistance to the off state, and the polarization switches back to the downward configuration. So we can have a quantitative agreement between the polarization configuration and the resistance by simply considering a parallel conduction through each of the domains. So now we can do dynamics by applying the same voltage pulse for several times. So this is a pulse of 1 volt, 100 nanoseconds. And we start from the on state here and collect polarization maps as a function of these pulses. So this is what we observe. So you see that we have progressive reversal of polarization as a function of these cumulative pulses. And we go towards the off state with a lot of integrated time. So we can also collect the resistance as a function of these cumulative pulses. And we see that we go also towards the off state. So from the images, we estimate the fraction of down to up domains, S equals 0 in the on state, and S equals 1 in the off state. From the resistance also, from the parallel conduction, we can estimate S, and we have a good agreement with the PFM observations. So this is to emphasize that even though PFM gives a lot of information on the domain distribution, we can simply do transport measurements to follow the dynamics of ferroelectric domains. And this is much quicker than PFM images. And so we can look at the switching at different voltages. Now this is the same experiment, cumulative pulse duration and different amplitudes here. And we follow S as a function of time. And you see that as we increase the amplitude, we have a sharper and sharper switching. To understand this effect, we followed what was done previously for thick ferroelectric films, and especially by the group of Taiwan now, which considered that there are defects in the films that are limiting the propagation of the domain. So we have a very limited propagation of the domain during the switching. And so what they consider here is the distribution of nucleation time as a Lorentzian. And when we use this model to our experiments, this fits quite well. So this means that we have a simple way to explain the trends that we observe in the dynamics in these ferroelectric tunnel junctions. Thank you. And also, so we collaborated with Bin Chu and Laurent Belesch in the University of Arkansas, and they did molecular dynamics simulations in this T phase of BFO, so in bulk T phase, And they observed that even at the local scale, the switching was not homogeneous, as it is the case, for example, for R-phase BFO. So there could be an intrinsic reason for this inhomogeneous switching in supertetragonal BFO. So now when we compare the results of the data of the experiments and the molecular dynamic simulation, in both cases we see that the switching time and distribution are increasing when we decrease the electric field, and we see that there's a unique dependence of the mean switching time as a function of the inverse of the field for molecular dynamics and the experiments. And this follows Mertz's law. So now we can understand the behavior of these devices. We wanted to see if we can implement a learning rule for these ferroelectric memory stores. And a simple learning rule is called a spike timing dependent plasticity. So this is a way to have the synaptic plasticity by considering the time difference between spikes that are coming between different neurons. So here we have a flow of information from the left to the right. There's one synapse in between two neurons. Each neuron is spiking, and depending on the time difference, the synapse will be more open or closed in a way. So here what happens is that if the presynaptic neuron spikes first, and then it is followed very quickly by the postsynaptic neuron, there's a causality between the two events. In the other case, where the postsynaptic neuron spikes first, there's no causality. And what happens is that in the first case, the transmission of the synapse will be increased. There's potentiation. And in the other case, it will be more resistive. Okay? So this is what is observed in biological systems. The data points here are collected in a rat brain. Okay? So this learning rule is quite simple, but it is believed to be at the heart of unsupervised learning in artificial neural networks. So it is a very important learning rule. So we wanted to implement this with our ferroelectric memory stores. What we do is simply emulate the spikes by voltage waveforms that we apply to our device. And depending on the time difference, we'll reach either a positive voltage threshold where the device resistance should increase, or negative voltage threshold where it should decrease. And so we did these STDP experiments and observed the following. So something very close to what I showed you previously for biological systems. So this is working quite well, and the different colors are different experiments on the device. So here we have a transmission that is increased and decreased depending on the time difference between these two spikes. And at infinite time, there's no evolution of the transmission. So we used our ferroelectric domain dynamics model to fit these STDP curves. And what we did is we combined it with hysteresis curves on the same device. So you see we can fit this data, and we obtain a set of switching time and distribution as a function of the voltage. So then we can use this physical parameter to predict new shape of STDPs. So you see here different input, different voltage waveforms that give rise to prediction of new kind of STDPs. And then we did the experiments on the device, and we obtained a very good agreement with this prediction. So we believe this is an important step towards unsupervised learning in artificial neural networks based on these ferroelectric memory stores. So in conclusion, I hope I convince you of the interest of these ferroelectric tunnel junctions to be used as artificial synapses. We can use the high sensitivity of tunnel resistance to probe the ferroelectric domain dynamics. And from the model we made, we can also predict the behavior of these synapse that will be integrated in large arrays of artificial neural networks. So just to mention, this field is not limited to oxides, and recently with Brahim Keel and Chinese colleagues, we showed also that we could have very nice results with tunnel junctions based on PVDF tunnel barriers. Thank you very much for your attention.
Thank you. Time for a few questions.
So in your tunnel stack here, you have, is that a magnetic underlayer? Is the metallic manganite ferromagnetic?
It's paramagnetic, yeah.
It's paramagnetic. So you have effectively some sort of a spin tunneling here too, right, at the same time? Do you see anything? You have a cobalt top electrode and you have this paramagnetic underlayer, so you're going to have some sort of spin-dependent tunneling through this BFO as well. So does the BFO exchange bias on the cobalt matter here?
No. We didn't look at it very much, but we did a few experiments where we applied the field in these devices. The changes are very small compared to what we observe.
So if you were to switch to like LSMO or something that's ferromagnetic underlayer,
yeah,
would you expect to have a combined ferroelectric tunneling memristor behavior with some sort of switchable spin torque device?
Sure. Sure, we are interested in this, but the difficulty here is to have this T-phase BFO and find an oxide electrode that is ferromagnetic and compatible with such a strain.
Okay, thank you.
Thank you.
Time for another question.
So for those intermediate states you show giving rise to different resistance, how stable are those intermediate states? And for this multi-state memory to work, do you require a stable intermediate? I believe you require some stable intermediate states, right?
So they can be very stable, but what we see is that the saturated states, the on-off states, are much more stable than the intermediate states. So when we look at the retention over days, over 3 days, the saturated states are stable, but the intermediate states relax a bit.
Right.
But for these kind of networks, the retention may not be so important. I mean, the length of the retention may not be such an important criterion. The most important feature here is really the plasticity.
Time for one last question. Not just, I mean, this is almost philosophical, but you demonstrate that there's a similarity in the behavior of the synapses now with biological systems. But surely the big problem is going to be wiring this up into a device.
Yeah.
Are there ideas on this?
So right now we require a high density of these artificial synapses. So right now we are working on crossbar arrays of these ferroelectric tunnel junctions, and this seems to work quite well. And we are collaborating with other teams in Bordeaux that are developing a chip where we have these artificial neurons that will be bonded to this. So, yeah, we are working on it.
Sounds fascinating. Let's thank the speaker again.
Thank you very much.
And we move on. The next speaker is Alexei Bokov from Simon Fraser University in Canada. And he's going to be speaking on domain wall dynamics in ferroelectrics by means of X-ray photon correlation spectroscopy.
Good morning, everybody. I will talk today about the dynamics of domain walls. You know that many properties of ferroelectric materials are based on the domain wall motion, and in particular on the motion of domain walls under external excitations. And if we are talking about the observation of domain patterns, we know that with the help of different kind of microscopy, we can readily obtain the images even on atomic scale of the static domain patterns, but the investigation of domain dynamics is challenging, and even even if we're talking about the dynamics, we usually observe the domain patterns and different steps of the motion, and we can hardly say what happens in between. Thus, in this work, we apply comparatively new method of X-ray photon correlation spectroscopy to study the motion of domain walls. This method is known for several years, and with this method, people study the dynamics in soft matter, polymers, and so on, but not in ferroelectrics. And we apply this method to study the domain wall motion in PZT single crystals with a composition close to morphotropic phase boundary. First of all, several words about the method. You know that usual observation of X-ray scattering is made on the radiation which is not coherent. The coherence length of usual X-ray is several micrometers, but in traditional experiments, we use the beam of the size of about 1 micrometer. Thus, to obtain coherent radiation, we need to cut small portion of this beam. Of course, the intensity would be small. Thus, to analyze the scattering, we need very high intensity of radiation, which can be obtained in modern synchrotron radiation sources. And this is the example of the difference between coherent and non-coherent scattering from one of the pioneering works in this field. The metallic alloy, we observe the 001 Bragg peak in traditional X-ray, and with the help of coherent radiation, you see instead of smooth peak, we see something like this, and in 2 dimensions, it would be complex pattern, which contains of spots called speckles. And this pattern is related to some kind of disorder in the material, because in the ordered material we expect Bragg peak, which is delta function, and disorder introduces such kind of complex picture, and the aim of the method is to observe the change of the speckle pattern during the time. Even if we have some changes in electron density, even on atomic scale, we expect that the pattern should change, and by analyzing these changes, we can observe the slow dynamics in the material on this time scale of several microseconds or slower. And this is the experimental setup we used, and a DAISY synchrotron source, Petra 3, And we studied 001 Bragg reflection, but not in exactly at the position of the reflection, but a little bit away from the exact position. And we studied the spot of this crystal with the size of about several micrometers, where the radiation should be coherent. And traditional approach is to analyze the speckle patterns at different moments of time at constant temperature, but we didn't observe significant changes, which is expected because of the solid state. Nothing changes at constant temperature. Thus, we apply different approach. We studied the variation of speckle pattern as a function of temperature rather than as a function of time. Thus, during constant cooling of the crystal, we observe the changes, and we expect that due to change of domain pattern or due to motion of domain walls, the speckle pattern would change, and we expect that the motion of domain walls would occur in monoclinic phase, but not in tetragonal phase. As we study crystal upon cooling from tetragonal phase, then in monoclinic phase. Why we didn't expect temperature-driven motion of domain walls in high symmetry phase? It is known that the position of domain walls is determined by the mechanical compatibility conditions, which is determined by the components of spontaneous strain tensor. And in high symmetry phases, this is the example, the domain walls are always parallel to crystallographically prominent planes like 001 and 011 plane. Thus, the domain wall is parallel to 001 crystallographic direction of 45 degrees. And the spontaneous polarization also goes through these directions. And when the temperature changes, the position of domain walls are not expected to change. The different situation is in monoclinic phase. Here, the monoclinic, the domain pattern in the monoclinic phase of PZT crystal, which we study, you see that the direction of domain walls are not 45 degrees or 90 degrees. And these are so-called S walls. And when temperature changes, we expect that the direction of spontaneous polarization would change with temperature, and accordingly, the position of domain walls would change. And we rarely observe the rotation of spontaneous polarization as a function of temperature. These are the data of polarized light microscopy observation of our crystal, and based on this data, we can extract the direction of spontaneous polarization in different phases of the crystal. Upon cooling, we go through the tetragonal phase, then monoclinic phase, and accordingly, spontaneous polarization is along 001 direction, then spontaneous polarization changes upon cooling, and then in rhombohedral phase, we have 111 direction. And accordingly, when the direction of spontaneous polarization changes, we expect that the position of domain walls also will move with temperature. And these are our observations. We observe the speckle pattern, temperature changes, you see, and the pattern changes. The Bragg reflection somewhere here is half a degree away from this. part of the reciprocal space, and we have a lot of speckle patterns. And the next step is how to analyze this picture. And we apply usual approach. We analyzed the speckle patterns at different speckle patterns and calculate the correlation coefficient between these patterns, so that where the patterns are exactly the same, the correlation coefficient equals 1, and in completely uncorrelated state, it is 0. Thus, again, this is a conventional approach. The difference is that we analyze different temperatures. And this is the result, the correlation matrix which we calculated. We compare two different temperatures. The diagonal, the correlation function is equals 1, and then when the difference between two patterns, the difference in temperature increases, the correlation function drops. Once again, the main reasons of the change of correlation function, correlation decay, first of all, this is the lattice strain related to spontaneous strain or crystal expansion upon temperature. And the second source is the domain wall displacement, domain wall motion, which is expected only in monoclinic phase, but not in trigonal phase. We again calculated the correlation decay at constant temperatures. It looks like this. It is known that usually it can be described by stretch exponential or compress exponential function, and we rarely observe this behavior, but the problem is that we observe this function only at very small temperature intervals. And these are the results for different temperatures. You see, at the beginning, the behavior is good, can be good fitted to this function, but not at other delta t. And as we have a lot of such kind of curves, we decided to apply a statistical approach to analyze this behavior. We plotted the histograms which show the number of counts at different delta t as a function of delta c. Delta c, this is the change of correlation function. And if we analyze comparatively large temperature intervals like this, we can see the histograms with sometimes with many mode histograms. Each mode we expect related to the motion of some kind of domain wall or some different domain walls. How to distinguish the behavior related to domain wall motion? We know that even in ideal crystal, the wall moves in some energy potential, thus the motion is like jumps or jerks step by step, and it is even more severe in crystals with defects. Thus, we expect that the motion of domain wall is and related change of correlation function is discrete variable. Thus, we expect that we can describe the motion with that histograms which I showed you with the help of Poisson probability function. And in contrast, when we observe the motion, the behavior in tetragonal phase where there is no domain wall motion, we expect Gaussian distribution. With some mathematics, we can extract the relation between macroscopic characteristics of the domain wall motion and the observed characteristics, and then the analysis. We showed that really the behavior in monoclinic phase follows the Poisson correlation, the correlation statistics, and behavior in tetragonal phase follows the Gaussian statistics. These are fitting to Poisson and Gauss functions at different delta t values. And you can see that tetragonal phase can be fitted well by Gaussian function, but not by Poisson function. And vice versa, in monoclinic phase, we can apply Poisson function. And furthermore, these several modes of in histograms, which are related to the motion of different domain walls we expected, can be described by different Poisson functions, several Poisson functions. You can see again the statistical development, and what is important when we analyzed the mean value and standard deviation in these two cases, we see that in tetragonal phase, mean value is proportional to standard deviation of that histograms, and in monoclinic phase, the mean value is proportional to variance, to the square of standard deviation. This is the known property of Poisson distributions, and this proves that we really observe Poisson distribution in monoclinic phase. And then, when we analyze the mean values of the correlation function extracted by such kind of fitting, instead of many very noisy curves, we observe single averaged curve. And these are some examples, when we analyze the correlation in some temperature intervals of monoclinic phase, we observe the change like this. When we try to apply conventional compressed exponential function to fit these curves, we found that it can be done only at small delta t, and we suggested modified function, which is different by this term. In this case, we can describe different mode of the correlation function very well, and extract the macroscopic parameters characterizing the process. Thus, in conclusion, we show that X-ray photon correlation spectroscopy can be a powerful tool to study non-equilibrium dynamics of ferroelastic domain walls, and we developed the method how to treat this process and show how to distinguish the dynamics related to the motion of the domain walls. It is described by Poisson distribution, and the other contributions can be described by Gaussian statistics. And we proposed the empirical function to describe the correlation function. Thank you.
Questions? One up at the back.
First, I'd like to maybe shamelessly advertise my poster, where we show this XPCS can be used for ferroelectric domains. It's in a poster. It's in a physical review. Second, what is the longitudinal coherence length of your X-rays? Longitudinal coherence length along the beam direction?
I cannot hear you.
What is the longitudinal coherence length of your X-ray beam?
What is
Coherence length?
coherent length?
Yeah, along the beam direction.
In of the X-ray?
Yeah.
Several micrometers. It is believed to be several micrometers, coherence length of the radiation.
The question is not just the lateral coherence length, but longitudinal in the direction of the X-ray beam. I think that's the question.
In the direction of X-ray beam, I think that I'm not sure. I think that it's enough to obtain the coherent radiation.
Yeah, typically longitudinal direction is very short, and unless you have a really special care is taken, your let's say speckle patterns are all averaged along the depth of your crystal. So unless you show there is a speckle pattern is changing in time, behaving normally as expected, then you won't be able to tell that actually this is actually speckles or not, because you're averaging so many of them. So it's something that had to be taken into account.
This is the beamline dedicated for this kind of observations first. And then, of course, we can observe some changes with time. But all these changes can be observed in both in tetragonal and in monoclinic phases. What is the difference? We observe different statistics in these two phases. Thus, this means that in monoclinic phase, when we expect the motion of domain walls, this is a different contribution.
Yeah, I think you should discuss in detail, the two of you, afterwards. There's time for another question just here.
Yes, we expect different contributions, but we extract the contributions related to domain walls, and which is observed only in monoclinic phase.
So apparently you need the statistical treatment just because sampling is bad with 5 microns illumination. And what will happen if you use visible light instead of X-rays with large
sorry, I cannot hear you.
What if you use visible light instead of X-rays?
Of course, we expect something like this with visible light, because in principle, the dynamic light scattering is based on the same physics.
Yeah, and you will have less troubles with bad sampling with small beam. So why doing that in painful way instead of simpler way?
Instead of visible light?
Yep.
That's, as I know, nobody studied this material with visible light.
Okay.
That's, if somebody will, it's okay.
Well, you are looking at some diffraction peaks. I mean, this is only possible with the X-rays, perhaps. Is there any other question before we move on to the last presentation of this morning's session? If not, let's thank the speaker again. And the last speaker is, I'm going to get the name wrong, I'm sorry. Okay, Bixia Wonga, who comes also from Simon Fraser University, and she'll be presenting a talk on nano and microdomain structure in tetragonal PZT single crystals.
Can I put it in my
You can put
pocket?
it in your pocket.
Okay. I think it's here. Okay, good morning, everyone. I'm Bixia. I'm from same group as Alex. Today, I'll talk about complex domain structure in tetragonal PZT single crystals. First, a brief introduction on why we choose PZT single crystals. As many of you may know that PZT ceramics, especially the compositions in MPB region, are the mostly widely studied electroceramics, but many aspects of their high performance in PZT is still not clear. So PZT single crystals are highly demanded for both characterization of the MPB structure and their intrinsic and isotopic properties. But the growth of PZT single crystals has been a big challenge for the ferroelectric community for so many years. And recently in our lab, we developed a top-seeded solution growth method. And this method enables us to successfully grow PZT single crystals with different compositions. Here is the furnace and crucible setup for this method, and that is the temperature profile we used. In this method, the seed crystal was put in at that point to trigger the nucleation, and the crystal out at that point. We also tried to use different chemical and thermodynamic and kinetic parameters and studied the effects of these parameters on the growth of PZT single crystals. By adjusting those parameters and the growth conditions, we were able to grow very good quality PZT single crystals with their compositions from 25 to 70% PT. Here are a few examples of the PZT single crystals we have obtained by top-seeded solution growth method. In terms of the property of the PZT single crystals, the best piezoelectric constant was found for the 46% PT single crystal, and the D33 value reaches 1223 picoulomb per Newton. The calculate K33 value based on this equation is 80%. And compared to the late Ferroelectric ceramics and PZT ceramics, this value is way much higher. So PZT single crystal is high TC, high performance piezo crystals. And compared to the PMM PT single crystals, even though the D33 and K33 value is a little bit lower, but PZT single crystal has a much large cohesive field and higher phase transition temperature. So it is potentially interesting for high temperature and high power applications. In most of applications of PZT ceramics, it's used in doped form, either by donor doping or acceptor doping. Donor doping could lead to cation vacancies in the structure, and the material with the cation vacancies shows high piezoelectric constant and smaller cohesive field, so they can use as softer ferroelectric materials. On the other hand, if it's accepted doping, it can cause oxygen vacancy, and we could make harder ferroelectric materials for high power application. In general, single crystals has much better properties than their ceramic counterparts. So in our group, we also tried to grow doped PZT single crystals by both donor and acceptor doping. In terms of donor doping, we've tried platinum and bismuth, and accepted doping, we tried magnesium and manganese. Here are a few crystals we've obtained. The domain structure I'm going to talk about today is for pure PZT single crystals. The composition is, the structure of the crystal is confirmed to be tetragonal by X-ray powder diffraction analysis, and the lattice parameter, nothing works. The calculated lattice parameters is very close to the 55% PZT ceramics. We also did dielectric measurement, and the phase transition from ferroelectric to ferroelectric occurs at 406 degrees Celsius. And according to this well-established phase diagram, the composition is around 54% PT. And according to that phase diagram, the composition should be in the tetragonal, the structure should be tetragonal, and that is inconsistent with the XRD results. Then we brought the single crystal to study the domain structure and phase transition by polarized light microscope. We polished a 001 platelet. But surprisingly, the 001 platelet is isotopic at, under the polarized light microscope. And a 011 cut sample shows birefringence on the polarized light microscope, and it shows extinction at 90 and 0 degrees. So that's the extinction angle for tetragonal symmetry. So these two plants are from same sample, but they give different symmetry. Why? Before I give my explanation, first let's look at the optical isotope in tetragonal phase. In a tetragonal crystal, there are three ferroelastic domain states, A, B, and C, and the orientations of the optical indicatrix are represented by three ellipsoids in that figure. So in a 001 cut planet like this one, we will have configurations of the indicatrix sections like this. And the possible ferroelastic domains with the corresponding configurations of the indicatrix sections in a 011 cut planet is like that. So it's on the top image. And usually in a crystal planet, we have so many domains stacking on top of each other. And in a 001 cut sample, if we look from top, we will have an overall effect like this. So in a 001 cut planet, the domains of mutually perpendicular extinctions are superimposed with each other, and that gives a zero net birefringence. But in the case of 011 cut sample, if we look from top, there is still composition, but it's not compensated. That's why we observed birefringence for the 011 cut planet. But this also indicates that the domain size in my sample might be very small, could be in nanoscale, sorry. And upon heating, the 011 cut sample undergoes a phase transition from tetragonal to cubic at around 406 degrees Celsius. And the birefringence vanishes at 406 degrees Celsius. We also tried to apply electric fields on the 001 cut sample on the on two edges of 0, 1, 0. And this is how the sample looked like before applied electric field. It shows it's isotropic without electric field. But once we apply electric field, the sample becomes brighter and brighter. That means the birefringence is increasing. Because the nanodomains are perpendicular to each other before, but the electric field can reorient some of them, so they are not cancelled out completely now. This is how the sample looks like at high electric field. In the meantime, we observed that square-shaped islands are showing up when we apply electric field. They are aligned in 110 direction, and the average size of these islands is about 12 micrometer. We suspect they are ferroelectric domains, so we carried out PFM analysis. And on the PFM, again, we observe these kind of patterns, square, and they are very similar to the previous observed islands in terms of orientation and their size. By applying an electric field perpendicular to the sample surface, we were able to switch the polarization of those patterns. So this confirms that those patterns are ferroelectric domains, and an electric field can switch their polarization direction. So combined with the previous data and the PFM results, we conclude that in this sample, square-shaped ferroelectric domains are embedded in a matrix of nanodomains. So here, in this region, the square region, we only have one domain, so it should be 180 domain. And in this region, there are tetragonal nanodomains. So we have both 90 and 180 domain. The arrows here indicate the polarization direction of the domains. For the formation of the square-shaped domains, our tentative interpretation is that a 100 circular small domain is nucleated in the tetragonal nanodomain region, and then it starts to grow with the different velocities along different directions. And because the velocity along 100 direction is much faster than the velocity along 110, so the domain ends up as a square shape. This also explains here, if we look at this pattern obtained from PFM analysis, the smaller size one shows more rounded shape compared with the large one. We also measured the birefringence change for the nanodomain region for this sample. And you can see that as the increase of electric field, the birefringence keep increasing, but with the different rates at different rates. Here, a lower rate, but there a higher rate at around this field. And simultaneously, here at this electric field, there's a jump in extinction angle. Usually, a change in the extinction angle means there's a new phase induced. So there's a new phase induced, and the extinction angle of this phase is increasing as the increase of the electric field. That is a signature of the monoclinic phase. So by applying electric field, we induce the monoclinic phase in the tetragonal nanodomain region. To wrap up my presentation, in this work, we've grown PZT single crystals from a composition from 20% to 70% PD, and the base piezoelectric constant we obtained is 1223 picoulomb per Newton with a K00 value as 80%. And this makes the PZT single crystal potential interesting piezo crystal for high temperature and high field applications. And availability of PZT single crystal allow us to perform some characterizations which PZT ceramics cannot. We've also observed the nanodomain and square-shaped ferroelectric domain in this sample. And a monoclinic phase is induced by external electric field. And thank you for your attention.
Thank you very much. I know you all want to go for the coffee break, but we can fit in a question beforehand if somebody's got one to ask. Yes?
How difficult it is to look at the birefringence of 111 plane?
111.
Yeah.
We haven't tried it. It's not difficult. We just need to prepare. Oh no. Let me look at the.
It's fine.
Let me see if there's birefringence. If we look at. So if it's a 111 plane, they might be cancelled out as well. You mean like the experiment, the operation, or whether I can see birefringence on this sample?
Right. It's much more complicated.
Yeah, so I need to, yeah.
Okay. Well, if there's no other questions, we'll thank Bixia again and all of the speakers in this morning's session. Just before you leave, organizers, is there any announcement? Or coffee break? Okay, we reconvene in half an hour.
Oh, I still, yeah.
How's it going? Just in the wrong direction. Never
Do you have HDMI?
Yeah, it is right here.
Okay.
Just plug right in.
Let me try it.
Yeah, sure.
Do I need to
Yeah,
disconnect that?
disconnect.
Okay. It works.